is my presentation about Snowflakes, about politics and science. Here's a little bit about me. I've got a name and a job. I went to university for too long, and I work for Landcare Research New Zealand, which is university for far too long. Landcare Research. Landcare Research is a crowd research institute in New Zealand, roughly equivalent to a small part of CSRO. We had one like it once, except we broke it apart and sold it. Apparently I'm also a responsible parent, but that's in Here's a little bit about Landcare Research. We're a public sector research organisation. We were formed in the New Zealand government, broke up DSIR in the 90s. And I worked for Landcare Research in 2009 as a systems administrator. And I worked in a number of projects. If I was to simplify what Landcare Research is, we did land-based science. We tell people what's good to do where the soil's good, if it's slopey, if it's soggy, if it's salty, and we help them figure out how to use the environment or how to protect it, depending on their point of view. Landcare Research invested in, as a collaborator, in the New Zealand e-science infrastructure, which provides HPC resources to researchers across New Zealand. There's a similar project in Australia based on Nectar. Are there hands up for anyone here from Nectar or affiliated institution? No, awesome. Oh, no, there's one. Thought there might be. I'm in particular affiliated with the group that works out of Auckland, running the PAN cluster, which is an x86 cluster, about 300 servers, and coming up to about 3,500 cores. I think we provided about, coming up to providing 30 million core hours to researchers across New Zealand in the past 10 years. And here we go. The thing that I manage inside NESI is a thing called NEE, which is the NESI virtual environment. This provides hosting of virtual machines that provide internal and external facing services to people within NESI and also to the researchers who are our clients. It's not as big or as grand as some of the other virtual environments that have been talked about today. We're only hosting 70 to 100 virtual machines, but there's some problems around them that make them actually a lot of hard work. One of the problems is research is not business. Our primary goal is not to make money or profit. It is to generate research outcomes. And we do that by going and asking people for money and then we spend it all. We don't keep any left. In fact, making a profit is such an alien thing to research that we put artificial structures around our researchers that skim cash off. Whatever they're doing, and that goes in to pay our overheads. They hate it. But what researchers do focus on is generating as many research outputs as possible for a particular research project. And what the outputs they're looking for is the most correct one, the one that is closest to the truth. Of course, scientists deal with uncertainty. They won't claim it is the truth, they'll just say it's close as they can get. And these mean that we are driven by a number of different forces compared to a company that's just in it for the money. I had to actually resort to Wikipedia to drag these things out, but the Bureau Shaping Law here pretty much says that the thing that gets researchers more money is their reputation to do research. So they will do things that puff themselves up. They will do things that give them a better research, they generate better outcomes, and more widely published, and more widely accepted in the community, and that gets them more money. It's not making a profit, and it's not having a return on investment. It's building a reputation. The budget maximising model says that you'll try and do as much work as you can with the resources you've got. You will spend every waking hour of your day doing your job. Researchers, proper academics, just trump you guys for working hours per week. They live their job their whole life. They may be going home and having tea and watching television, but in the back of their head there's something going on figuring out how they can better model house pee and paddocks. This is actually something we do at Landcare. And Parkinson laws covers that. No, I skipped that one. Yep, here we go. Okay. What I'm trying to say is that the culture that I'm working for is different from the ones that you're probably working for in the corporate or capitalist or business environments that you're working. What does this mean for IT? Well, it means that my IT environment is unpredictable. Researchers want to do many different things because the different things give them the comparisons that generate new bits of knowledge that they then publish to build their reputation to get more grant money. And the other part from that is correctness trumps efficiency. They don't care that it might take days to run a certain job, provided that the number that they get is the right number. The output is the correct output. So you can say that you might want to make your algorithms run faster, or you might want to say you could do this for less money. That's not effective if it doesn't actually come out with the correct result. Bleeding edge technologies. Scientists always working on the latest versions of what a bit of software package they want to use. They will get the one that's got the bug that fixes the problem, that does not fit the code, and if there is a problem with the code, they will fix it themselves, and they may or may not publish it back to the community. This means that the technologies that they are using are extremely unstable, and this includes the things they run on their computers. Things are under constant change, because of course they're trying to establish what changes causes new knowledge to come out, so they can exploit that. So they will be constantly tweaking their systems to try and find these places where they can generate new research outcomes. We also have a problem that we have no two similar machines. Even though there are two machines doing roughly the same role in the same project, made by the same person, again they may have engendered some small change between them that gives them that difference that generates new knowledge, again, and that generates research. We also have a problem with secrecy. These systems are only accessible to the researchers and their teams for the duration of the research project. This is reinforced at the moment for several reasons. Research outcomes often form intellectual property that can be commercialised. Research outputs may contain sensitive information such as medical data and private data. And generally research is under embargo until they publish it. But it's also contradictory. Sometimes instead of being unpredictable, it's routine. They want to be able to do something over and over again to be sure it comes out exactly the same way every time. And these days, this may not mean running it over and over again on the same machine. They may come to a group like NESI and they'll run their algorithm 100 or 1,000 times across the cluster. This means we have to actually get their thing, which may exhibit all of these terrible and unpleasant properties, running it on our system. Efficiency trumps correctness. When you're doing it routine, you actually do want to do it as quickly as you can. So you then have to go through the process of optimizing their models and their applications so that it runs more efficiently on your system. They won't be interested in doing that. So you have to actually help them there and provide resources to do that. Legacy technologies, just as often as they're asking us to provide us a service that was released last week, they will say, I need to run something that was run in 1986. And then they'll want to do a cross-comparison of the new thing versus the old thing. This is because science and research is done by intergenerational institutes. Landcare research has been around for since 1992. Before then it was part of DSIR, which goes back to the Soil Bureau, which eventually gets back to about 1860, where they surveyed New Zealand for the first time. At the same time as we are in constant change, they want to minimise change. When they get to this stage, which is usually a later stage of a research project, they want to make sure that it continues to deliver this correct output. So they don't want to make changes because they want it to stay as stable as possible. Yeah, they are terrible people. Reproducibility. Just when things weren't getting bad enough, they start saying they want other people to reproduce their work. And as you can see, they've done a great deal of effort to make it very, very hard. And then transparency. Transparency because they'll then want to publish it. Now, what I'm saying in the context of research, computers are research tools. They're no longer general purpose computing machines, they're instruments of science. These are a couple of interesting examples here. Is on the left side, you've got what was a scanning electron microscope and the computer that was on the side that people used to harvest the pictures that they took at one of these Snowflakes. This is what they look like now. That box on the side isn't just a scanning electron microscope, it has an embedded PC inside. The technology of the scientific instrument has kept pace with the technology improvements you're seeing in the PC that sits on your desk, and now they both sit on your desk. Not the thing over there the size of a washing machine. My laptop, as a researcher, is an instrument of science. I use it to do a kind of science. It's not quite the same as the researcher. And I keep track of how I got it set up, because unlike myself, my laptop is replaceable. I need to be able to recreate it when it eats its hard drive like it does, or I get a new one which my company provides for me every 3 years or so. So I use tools and documentation to get together to put it together. We're trying to encourage people to try and automate that, and we know what we can use to do that. And but it's just a starting point to show that these are all scientific instruments. And to manage these, researchers, the guys on the left, require enablers of research, people who help them to keep things going on the right. So they're over there talking about research, and here's him keeping the fire going so it works in the context of IT, those are developers, and this is the opposite. So we're talking about adding to the enablers of research software developers, systems administrators, and DevOps. These people are already engaged in large-scale scientific processes. CERN is quite a good example. They're using a lot of the technologies that we're using here, Popup, OpenStack, and the rest, to automate the deployment of a phenomenally large amount of machines to handle inhumanly large amounts of data. They just can't keep it all. Unfortunately, some of their scientific outcomes are the results of systems administration problems. The recent event where they described superluminal neutrinos is because someone hadn't plugged the cable in correctly. And you can guess which person on the IT team is going to be querying about that. I skipped something. Right. What I was meant to say before this slide came up is that when a computer first arrived at a research team's desk, it's delivered to them by the IT team at the institution, where they have probably used some kind of deployment system to deploy a static image onto that machine. And it's set up so that it's secure, it's well behaved, it integrates with the applications and services provided at that institution. And then it's handed over to the research team who's working on a research project. From that point, change happens. Lots of change. They'll hook it up to scientific instruments. They will install applications and software packages. They'll write scripts, and they will make changes almost constantly and still starts doing what they want. You know, very, very bad at recording and how that happens. So, what's the result in Snowflakes? This is something that we can agree on as a difficult thing to manage, and we're trying to improve this. Fortunately, there's a similar concept in science. It's called black boxes. And these are scientific instruments that you provide an input, which stimulates them, they do some work, and they get a response. The problem with the black box is you've got no idea what's going on inside. Another difficult problem with black boxes is that people who set them up often part of the black box artifact themselves. They may be keeping secrets, they said before secrecy, so that it's difficult for people to see inside that machine before they are ready to do it, in which case they'll forget what they've done. And as an observer, you're also part of the problem if you start using these things blindly because you're not questioning what's going on inside. At the moment, a lot of people are replicating them. They're either packaging these machines up and sending them off to people who ask for them, or they're giving out instructions on how to set them up and providing them with a a disk image or some way of installing that on a machine, or quite commonly these days they are distributing virtual machine images. This unfortunately just replicates the problem that these are black boxes that respond to stimulus, they give an output, and still no one's got any idea what's happening inside. This situation is the least trustworthy method that you can probably think of in science, because it's often exploited by people who are doing questionable science, and the often tells that you get from that is they will say they will provide you with a machine, but it has to have an operator who will provide it to. Or someone who's gone through certain training or certification will provide them as well. And these are usually scams. Science is yeah. Right. So there's a quick summary of research computers that we observed. There's Snowflakes. We've got no similar machines. There are inexplicable requirements for researchers because they have to meet the needs of their research and not business needs. The formally described implementation is often missing, but is required when they publish it. Change control and change records don't exist, but it should when they want to share the machine and they want to publish that as well. Each machine needs to be replicable for when they reproduce it, when they want other people to repeat their work for them. It needs to be transparent so that you can trust the machine, you can see what it's doing. It has to be transportable so that you can give it to other teams for them to work with and continue development of your science, the domain of your science. And then it has to be publishable, because eventually it's going to be put up somewhere that can be peer reviewed, which builds the reputation of your company, that gathers you the grants for research. Okay, I think we might be getting on to bits about Popup. This is going faster than I expected. Why do I care? Why do I care? I'm the system administrator. I'm the person who works for a company that provides, well, it's not really a company, it's work for an organisation that provides you with a resource, which is computing resources. I will be asked to take the model of this, the model that someone has set up on their laptop or server under their desk, or some terrible thing that they bought on Amazon AWS and set up on the cloud, and we asked to make it work on the cluster. So this often is done forensically. If you take the machine apart into tiny little bits and put it back together virtually in a virtual machine in our virtual environment, or we recreate all the applications and distribute them across the cluster using various tools, and then we run it again and again and again. And that works terribly. To be honest, where were we going? Yep. The right question is, do I care? No, I don't want to. I don't want to know I keep in mind all the details of why your machine is the way it is. I want to be able to describe it once and be done with it. Otherwise my brain will get full and I'll have no space left to do any other real work. So I don't want to remember that a certain machine needs to run Python 2.5 for the weather to be correct, because that's what you want to use. I don't want to know that the Possum model requires this particular graphics rendering package to be compiled with these options and with these additional libraries and with these patches that you've come up with. I don't need to know that this machine running Linux has to run a C# application, which I do, because this is how we model the aquifers under the Canterbury Plains in New Zealand. I don't need to remember that this SCSI drive on this device is not a drive, it's a satellite dish. These are things that I have to deal with. I haven't solved all of these problems with Popup, but these are problems that we have to consider, and as outrageous as some of those seem to be, they pop up every time we take on a new project from a new research team who are trying to do new and exciting things. So, we use Popup. We use Popup to describe these machines so that we have a formal description of each of these snowflakes. We use the domain language to go through with the research to ask them what they did, how they did it, what does it mean, is it important. So in our Popup manifests, we will have a collection of files, packages, services, and these are all very useful and ordinary things, but some of the files we've got from unusual locations. Some of the packages come from our custom package repositories, where we have packaged up their patched and special software, very special. We also use Git on these Popup manifests, and we use version control to manage the change and to segregate things out into branches. And in each branch, we can put the different, isolate the changes that they're putting on their own systems to get those bits of information that generate new knowledge that results in research outcomes. So by using Puppet, we've described the insanity of the various Snowflake machines, how badly configured they really are. And then by using Git, we've put these nice, use the branches to form cages around them so they isolate them into their own little spaces. And then we've got the commits that describe the individual piece of insanity as it comes down through the pipeline. So what we now have, we've turned Bedlam into an institution. We now have the inmates in their cells, which makes the task manageable. Okay? Now, this is a problem for us when we are recruiting. When we are asking for people to come into IT, we're not looking for people who come in who have gone every day and made progressive changes to a system and ended to a goal because it's regular, ordinary work for them. We're looking for people who, when they're dropped into the deep end of a pool of knowledge that they never worked with, have managed to cope. They've displayed adaptability and they've not sunk, they have swum. So when it's hard. I'm one of the few people coming up here and saying we're not hiring at the moment because our contract is ending and we won't be getting another one for another year. Right. What we now have in our environment, okay, sorry. This is the second part of my talk, and it's kind of a continuation on. We now use Puppet and Git within Neve to manage the virtual machines that we've created from the researchers, as well as the ones that we use to provide the services that we provide internally to NESI and externally to the NESI customers and clients. This allows us to reuse solutions that we've come across for all the problems, because even though scientists think that they're all doing everything their own special individual way, often that's not true. It's just that they put them in different combinations of permutations. So we don't always see the same problem. We often see the same problem repeatedly between them, but they've never talked to each other to figure out that it's the same problem between them. So the Neve Puppet configuration uses Git to manage different branches, and each of these delivered to different machines. So I can actually say that we use Git to manage dynamic Puppet environments, and it's clipped off the top of my script. But that's okay. I'll be giving them the PDF it's here. This is a script that we use in our Git server on our Popup repository, and it sits in the hook scripts. It's in fact, I think it's the post-receive script. We have another script we do on pre-commit, which does things like Popup lint and Puppet. Yeah, Puppet lint. And does a Puppet parser validate over each of the scripts as they come in and rejects broken or erroneous scripts. And this is the ones that go through that simple test that then replicates it over to our Puppet master using SSH. So it passes with this SSH from the Git user on the Git machine to the Puppet user on the Puppet machine, and then pushes it into the appropriate branch directory in the Puppet environments directory. It works pretty well, except that we did this bit here where we had a lot of our Puppet modules as sub-modules in our Puppet repository, in our Puppet manifest. This isn't the best idea. Works quite well when you've got a dozen or so Puppet modules, but eventually the complexity of Git and the complexity of managing Git sub-modules hurts you lots, and you have to keep going into your Puppet master, into your environments directory, and deleting and recloning your environment. This kind of breaks the fact that this is mostly an automated push system. So I would seriously recommend changing this to use Tim Sharp's library in Puppet. It's Tim Sharp's, and figure out what to do in this part here. I'm working on that, I just haven't finished it. So I can't tell you. From this, we've managed to generate a Popup workflow. We don't do this consistently or well, and often the people in the various roles on the side here are the same person. But I can tell you that the approver is the only person that allows changes made by the developers and approved by the testers to actually go into our master Puppet branch that goes into production, which we call live, because when it comes to research machines, it goes into real things production. Because you can never tell when a prototype was suddenly declared as a finished object and handed over to be commercialised or commoditised. Right. But by using Git, we allow the developers to independently work on different aspects of our Puppet management to make changes without interfering with the other parts of our system. I think you may have heard variations on this theme through the other presenters earlier today. But let's see what I've got. It starts with the developer wanting to develop a new feature or upgrade a service or something that he wants to improve on our environment. So in our virtual environment, we'll have a number of live machines, which are there in yellow, which are running live services, which are publicly accessible or currently producing outputs that are going to be consumed by other people. We have our test servers, which are used to do approval testing, and most importantly, they're used to test our public configuration. And then we have a development machine, which could be a virtual machine that we're hosting, or it could be something that exists on the developer's laptop, provided, of course, that it's puppeted. The developer will pull the master from our Git repository. They'll create a branch for the new feature. They'll do some development work on their branch. They will push it back to the Git repository, where some tests are done. This is where we don't do enough. Currently, our tests simply just doing syntax checks and style checks on the submitted Puppet code. But this is also where you modify that hook script so that it pushes the code off to some other facility to do continuous integration testing. So you can push it to the Jenkins server where Jenkins will go for its things. Or you can do tests using the other technologies I mentioned, Cucumber, Aspect Puppet, Aspect Server. And then once they're approved, they can then be moved on to the Puppet Master. And this is done as a push. It's done through a Git pull, but it's actually pushed. The Git repository will SSH to the Puppet Master, initiate a Git pull into the appropriate environment, creating a new environment, which is then deployed out to the development machine, and everything's okay. The problem we have is developers bypass this all the time. And it's actually fundamental to their job. They actually need to be much more agile than the system is, because the job isn't to make the system, it's to develop the feature that they've been asked to develop. Then we come up to the testing phase. A tester comes in, they will pull the developer's branch, they will have it set up on their machine, they will examine it, and this is where they need to talk to each other. It doesn't always happen, but it helps a lot if they can actually find out what the developer has done and what the tester is observing. The tester could be doing any number of things. He could be going through user stories, he could be going and checking that the green lights on the various machines have come up. Whatever, it's not actually important. What he's doing is making sure that what the developer's done fits the constraints of the system for something to be put into the live environment. Would include the things like the security testing that we did before. The tester then, probably in conjunction with the developer, will modify the Puppet environment so that it meets the tests and passes them. Again, that gets pushed out. The Git repository, test to run, and it'll probably pass because it's passed those tests before. It's then pushed out to the Puppet Master, merged into the test environment, which then goes to the test machine. But changes to our test environment don't just go to the test machine, they go to, oh, wait a minute, I skipped a step. Hopefully, by going through this process, you've eliminated the bypass. Here we go. Which means now everything you need to know about the machine is in the Puppet manifest, and the bypass has gone away. The other benefit of the testing environment is that all tests go out to our test machine. So another machine in our Puppet environment that would be affected by the changes that a developer and tester would have made also receives that change, which means you now have benefited from the work of this change of a single feature on more than one system. So if the developer and the tester decided to upgrade a package, or they decided to upgrade a Puppet module to a new version, or they've added a new feature to our entire Puppet manifest to improve security, this then gets pushed out to all our test machines to check if it causes anything to fail. This makes people a lot happier, very quickly. The first few times when this goes out and machines are fine, that's okay, they think it's not working. And then one day they push out a change and half the test environment falls over, and they then go, oh, that didn't go live. So they go back and they do it all over again and everything's happy. But canaries, you've got to have canaries. Then comes deployment phase, and you have an approver, and this is the person who has the golden keys to the master branch, and they go through a very similar process. They pull the branch, they talk to the other members of the team, who says, we've got a new feature we've deployed. The tester says, well, while we did that, we found a package that needed upgrading, and it gets approved. It gets merged to master, it gets pushed to master, it gets tested again, because we do that every time, because it's automated. Not tested, but it's automated. Pushed out to the Puppet master, deployed to the master branch, which is the production environment, and then that gets pushed out to all the live machines that can benefit from the change. So what we end up with is a general improvement of our environment, where we have a new feature deployed where it was intended. We have the collateral damage of an upgrade that's applied to all machines that benefit from it. But we also have our test environment running these new features and these new updates straight away. So our live environment and our test environment keep the same. This works quite well. The bit that we have a trouble in is convincing the developer to pull again from master when they come around to add another feature to their feature chain. And we're moving towards proper configuration management. We have good change control, we have good record of changes, because everything you've done either ends up as a record of work in your Puppet manifest, or as a record of change in your Git commits, and which you can then observe by reading through them or visualizing them in your repository web application. We use GitHub for the ones that we share publicly, and we use a private Git repository for those that are internal only. Currently our Git manifest is full of things that we don't want to share, like keys and passwords and URLs and all the rest. So we're going to be looking at using Hera to take them out of it. We don't want to put all of the machine state into Hera, because we want to use the Puppet manifest as a record of work, a comprehensive record of all the changes that we've done to our system, so that we can extract it and use it to publish when the researchers ask to publish the machine. So we're going to just use a Hera as a keeper of secrets. Other things that we use Puppet to do is we use Puppet to install Git, because often that's missed out. And you'd be surprised at the number of things that fall over when Git's suddenly not found. We also use it to deploy keys and certificates, and not just deploy them, we also use it to update them and revoke them. We're trying to think very hard about how to get Puppet to check if they are going to expire, but I don't think that's Puppet's job, that's our monitoring system job, which is down further. We're also looking at how to automate that a bit more, so that if a key isn't provided, it generates on the fly a self-signed key that lives on the Puppet master. Our intention is that the machine, a stateless machine is destroyed and redeployed. It will get its keys directly from the Popup master. So for all intents and purposes, it will be the same machine as it was before. We use it to configure custom package repositories for getting apt and yum packages that contain all of the software provided to us by our researchers. We use it to set up the user environment because you could believe that these bunch of collected individuals that we do research with all want to use their own particular settings and configurations. It also keeps the blind Emacs users because they can't see each other. Keeps them happy too. We also use it to set up our authentication because we have more than one authentication pattern in our Popup server depending on intended delivery orders. You can believe that we don't use the same authentication pattern on machines that require access by students to machines that require access just by academics to machines that just require access by the systems administrators. And even then, that's again made more complicated by the fact that we are collaborating with people from outside our institutions. So we need Radius to authenticate them when they've got those little USB keys they plug in. And we use this wonderful thing called Shibboleth, which is a federated single sign-on service. Only works for web application. So we have an extension that we have of the Popup Labs Apache module that installs and configures Apache use Shibboleth. We use it to configure logging and monitoring. We do an okay job of it at the moment. We could do better. For a start, it doesn't look as significant. We also use it to install Ruby because Ruby and developers and package maintainers don't get along. And systems administrators stopped compiling from source in the 90s for a good reason. Ruby developers haven't quite caught on to it. We also use it to install and configure Puppet. 5 minutes. We also use it to install and configure Puppet, which, you know, I thought that would be obvious to everyone, but apparently no. We use Puppet and Augeus to make sure that various settings in our Puppet conf are what we need them to be. We use it to tell different machines how often they should do their Puppet runs, some 5 minutes, some 30 minutes, some once a day, to account for the fact that some machines we want to keep a close eye on those small changes and some machines we want to remain fairly static. We also use it to make sure things like plugin sync is set and that they are actually pointing at the correct Puppet. Also because people tend to try and break it about Puppet conf and break it because they want to stop changing their machine. And that's usually because they're trying to do something with SSHD conf. We don't want to do that. Okay? Thank you all for listening.
Any questions for Aaron?
No?
More of a statement. You said you want to move sort of secret stuff out of Puppet manifesting into Hira, but aren't you going to keep that Hira stuff? So you didn't want to inject. Aren't you going to keep that Hira stuff?
Yes. We would keep that Hira configuration in a Git repository, but that would be a private repository. If we can extract those secrets and put them in Hira and keep them out of our Puppet configuration, we can make our Puppet configuration public. We can let people come and look at it and comment on it. And this is particularly important in the research community where you're trying to promote open science, open data, and open source systems. You want to be able to say, you don't want to have to go away and say, I'll get that ready for you. You want to say, just go look, here it is, here's how we set it up. You can do it too. We are currently using the open source version of Puppet, but if we get that over that jump, we can then start considering using Puppet Enterprise and then advising with other members of our community to use the open source version.
Any other questions? Thank you very much, Aaron. Appreciate that.